This is a quick lecture on chain rule. This is the formula for the chain rule. It states that g is differentiable at x and f is differentiable at g of x. And they're doing that because they're getting ready for a composition. So in that composition, what we have is they define a new function f, capital F, which is f composed with g, or can be written as f of g of x. And assuming that this is differentiable, well, this is going to be differentiable if these conditions above are satisfied, then the derivative of capital F is little f prime evaluated at g of x times g prime of x. So using Leibniz notation, it looks like this, but we have to warn you that this is not something that you would think about as a couple of fractions to cancel. Like the du's here don't cancel. So just keep that in mind. And what we're going to do is we're going to use this formula, carry it around with us, and use that to take the derivative of things. Here's our first problem. Let me put the formula up here. The first problem says consider the following function. Write the composite function of the form f composed with g by identifying the inner function u, which is equal to g of x, and the outer function y, which is equal to f of u. So what we have to do is when we're looking at our function, we have to kind of focus on what our outer function and our inner function is. So usually I like to start with the outer function, and the outer function looks like it's a square root of something. So if we focus on what is that something happens to be the inner function, which is what they're calling u. U is going to be equal to 8 plus 7x. So if we break this down and write y, actually we got this kind of twisted around because I like to look at things from the outside going in. The u function is already a function of x. So u is equal to, I'm just going to rewrite this whole thing, it looks like. So that's our answer, 8 plus 7x for u. And then y is going to be the square root of star, or square root of u. And that's our function, that's the variable for our outer function. So the square root of u, that's a function of u. So to find the derivative of this, if we imagine that this is g of x and this is f evaluated at u, then according to our chain rule, it's going to be f prime evaluated at g of x times g prime of x. So it looks like we're going to need f prime, and for now let's call it f prime of u. Well, if we rewrite this as u to the 1/2, then the derivative of that is going to be 1/2 u to the negative 1/2. So that's f prime of u, but we want to evaluate f prime of u at g of x. And what was g of x again? G of x is equal to this. So then f prime of g of x is going to equal to 1/2, and then instead of u, I'm going to replace that with g of x. And what is g of x equal to? G of x is equal to 8 plus 7x. So this is my first value, first component. The second part is going to be g prime of x, and this is g of x. So the g prime of x is going to be the derivative of this. It looks like it's just going to be 0 plus 7 times 1, or 7. So there is our answer. Our answer is going to be 1/2 8 plus 7x to the negative 1/2 power times the derivative of the inside, which is 7. And that is our derivative. Alright. Let's take a look at another problem. And let's see if we can start doing this a little bit more efficiently. Outer function and inner function. So the outer function, let me write this down here this time, y is equal to tangent of something. And that something we're going to call u. So why don't we just do that now. And then u, that something is going to be the cosine of x. So those are our values. Now we want the derivative. Remember our derivative formula. That looks like this, where we need to find, oh wait a minute, let's label these things appropriately. This is f of u, and this is g of x. So that's just copying those labels that they have. Now we want f prime, did this in red, f prime of u, the derivative of tangent is secant squared of u, and if you didn't know that, just make sure when you're doing these problems to have a table of integrals handy so that you can get through these problems a lot quicker. Now, according to the formula, we want to replace u with g of x. And what's g of x equal to? G of x is equal to cosine x. So this is secant squared of cosine of x. Now the other part that we need is g prime of x. So g prime of x, well, g of x is just cosine. The derivative of cosine of x is negative sine x. And there you go. So according to our formula, this should be equal to f prime of g of x times g prime of x. So that is the secant squared of cosine of x times negative sine of x. And so because of these minus signs that might be popping up in your derivatives, it might be important to make sure you use your parentheses wisely. So there might be some trick to simplify this, but we're not going to get into that right now. So let's just leave our answer like this. And remember, when you're doing derivatives, it's best to leave your answer in a simplified form, unless you need to go further with your derivatives. Okay, same problem, or same type of problem. It's a composition, and so we're going to use a chain rule. But this time, let's try thinking about working from outside in. So here is usually the phrase that I would be thinking about. First, we'll take the derivative. And then multiply by the derivative of the inner function. Now, thinking about it this way, you just have to be careful to keep your eye on the original problem. this is our original problem right here. Now, they have an a to the 6 here. We have to just treat a as a constant. So take the derivative of the outer function and then multiply it by the derivative of the inner function. Okay, let's see what we can do about this. So y prime is going to equal the derivative of cosine of something. The derivative of cosine of something is negative sine of something. So let's say a to the 6 plus x to the 6. So that's the derivative of the outer function. Now we're going to multiply and take the derivative of the inner function. And for the inner function, we have to know that this is the inner function right here. So the derivative, and some people do this, d dx of the inner function, that's a to the 6 plus x to the 6th, which would be fine. And then you'll just have to rewrite all this other stuff over again. And so the derivative of a to the 6, since a is a constant, any number raised to the any power is still going to be constant, so the derivative of that is 0. And the derivative of x to the 6 is 6x to the 5th. So just tack that on as a product when you're multiplying, and then you are done. So the derivative of the outer function, and then just to be absolutely clear, derivative of the outer function, and then we have to evaluate this at the inner function. Which means we're just going to put that inner function into the sine of whatever that we've got. Alright, so that's it. In this example, we have a chain rule. Within a chain rule, we're going to have to use the product rule. So let's go back to this statement over here. We take the derivative of the outer function multiplied by the derivative of the inner function. Now the outer function is something to the 4th power. So that's easy enough to do. It's going to be 4 times that something to the 4 minus 1 power. And what is that something? That something is evaluated again at the inner function. X squared plus 6, x squared minus 6. So this is the derivative of the outer function. Now I need to multiply by the derivative of the inner function. Now the inner function looks like it's a quotient, so we'll have to do the quotient rule. So this is a low, x squared minus 6, d high, derivative of x squared plus 6 is 2x, minus high, x squared plus 6, d low, derivative of the denominator is 2x, all over low squared, x squared minus 6. Now there are ways, x squared minus 6 to the 3rd power, to the 2nd power. Now there are probably ways to combine this and simplify it a little bit, but like I said, if this is all you need, if all you need is the derivative, then you are done. And the less you do with this, the better it is to grade, the better it is to not make any more algebraic mistakes, etc. Okay, here's another example of derivative. This time, this is the big picture is a quotient, and then within taking the derivative of each of these numerators and denominators, we're going to have to use the chain rule in there. So let's think about it as a quotient rule. And then chain rule inside. Or chain rule within the numerator and within the denominator. Alright, let's take a look at this problem. Let's go directly to the y prime. So we'll treat this as a numerator and denominator, low d high. So low, let's start off with e to the 3u plus e to the negative 3u. And then the derivative, and let's do this carefully, and I'm going to add extra steps here that you may not need, but I think it would be good to do this when you're first learning how to do these derivatives. E to the negative 3u minus high, e to the 3u minus e to the negative 3u, d low, so d dx of the low, e to the 3u plus e to the negative 3u, all over e to the 3u plus e to the negative 3u squared. Okay, so this is the quotient rule, and now these things need to be worked out and simplified. So let me rewrite everything over. E to the 3u plus e to the negative 3u times, now let's take the derivative of this thing. The derivative of e to the 3u. So remember that the derivative of e to the x, if you have your formula list, is equal to e to the x itself. And now, since this is more complicated than just a regular x or just a regular u, you have to take the derivative of the inside. So the derivative of this is going to be e to the 3u times the derivative of the inside, which is 3, plus, now the second one is going to be, oops, this should be a minus, and this is going to be e to the negative 3u, and then by the chain rule we need to take the derivative of the inside, and the derivative of the inside is the inside technically is negative 3 to the negative 3u, and the derivative of negative 3u is negative 3. Alright, so that's that first one. That's a derivative already figured out. And then minus, now this one remains the same, e to the 3u minus e to the negative 3u. Now we want to take the derivative of this. So this is e to the 3u times the derivative of 3u by the chain rule, plus e to the negative 3u times the derivative of negative 3u, again by the chain rule. And this is all divided by the same denominator that didn't change, e to the 3u plus e to the negative 3u squared. Okay, and I think this is done. Okay. All right. In this problem, we will need to apply the chain rule several times, more than once. Let's put it that way. So remember what I had mentioned earlier. Take the derivative of the outer function multiplied by the derivative of the inner function. Now, if there are more inner functions, like in this case there is, then you just need to keep multiplying by the inner function. Let me see if I can write down that formula. If your y is equal to f of g of h of x, it's kind of strange to write it that way, but that's exactly what's happening here. And I will identify the f, g, h, etc. So your derivative will be f evaluated at, or f prime evaluated at g of h of x times the derivative of the inside, which is another chain rule. That's g prime of h of x, and then times the derivative of the inside times h of x. So this is a chain rule that's happening in 3 layers instead of just 2. We can identify our functions exactly how they are. Let's call this, maybe let's call this v, and let's call this u. So the outer function f of v is 3 being raised to some power, and that power is going to be sine pi x. So this is your original function. Your next layer function, we're calling here g of x, or g of u, is going to be sine of pi of x, and so that's pi of x, or pi times x is what we're going to call u. And then u is our inner function, h of x, and this is pi x. So you see now this is 3 layers deep, and you're using the chain rule to go through those layers. So when we take our derivative, we need the derivative of these things. So let's do that off to the side over here. Let's do it down here. So f prime of v is the derivative of 3 to the v is itself again, like an exponential function, times ln of 3. So that's the first derivative, and then according to this formula we're going to replace it with g of h of x. What is g of h of x? It's g composed with h of x, or if we look at it, it's just the inner function, which is also a composition. So why don't we put that down here already? F prime of g of h of x, which is exactly what we're looking for in this first part, is equal to 3 raised to v, which is sine pi x, times ln of 3. It's the first layer. Second layer, we want to find g prime of u. Now g of u is sine u, g prime of u is cosine u. And what are we really looking for here? And we're going to replace u with h, which is pi x. So this is cosine of pi x. So that's our second layer. Our third layer, u, which is h, is just pi x, so the derivative of pi x is just pi. Pi is a constant, imagine that's like 3. Derivative of 3x is 3. So here we don't need to, oops, I forgot to put this prime here. Make sure there's a prime there. So this last bit over here is just h prime of x, and we don't need to include anything else in there. Alright, let's just finish off this problem. We have y prime of x is equal to f prime of g of h of x, which is 3 sine pi x ln 3 times the derivative of the next layer, the inside. This is a cosine pi x times the derivative of the inside of that, which is pi. So this looks okay as long as it's clearly being multiplied. I don't see any negative signs anywhere that might get things confused, but just to be absolutely sure, you can put brackets or parentheses around each of those factors. so that we're making sure that we're getting it all complete. Okay, so this is a 3-layer chain rule. Alright, let's go to another problem. Here are a couple of 3-layer chain rules that's being added together. And so the fortunate thing is that when we're taking the derivative of a sum, we just take the derivative of each of these individually and then put them together. Now, I'm just going to go with this kind of like this mantra. And if we want to include multiply by derivative inner function, let's say multiply the derivative of the next level function. And let's say, and so on, if there are more levels in your composition. So let's see if we can do this, and I'm going to try to do this without looking at the formula or anything. So let's just focus on each of these things term by term. F prime of t, so that's the derivative of the tangent of something. Derivative of tangent something is secant squared of something, and so that something happens to be e to the 2t, times the derivative of the inside, derivative of e to the 2t. So the derivative of e to the 2t is e to the 2t times the derivative of the inside, which is 2t, and the derivative of 2t is just 2. Okay, that's the first one. The second one is e to the tan 2t. So the derivative of e to something is e to that something, and we don't usually put parentheses here, but just so it's clear, we're going to put the parentheses here. Times the derivative of tangent 2t, which is secant squared 2t, and then times the derivative of 2t, which is 2. Alright, so a couple of chain rules problems, 3 levels deep, and this is our solution. So next one, I like these types of problems because I am really concerned about making sure you're able to distinguish between a product and a composition. In this case, we have the cosine of cosine of cosine of x. Now, it looks like you're multiplying 3 cosines together, but you're not. This says cosine of something, and this something is not a product. You're taking this term in here, and that goes inside of this cosine function. So this is not multiplication, this is composition, and this is a job for the chain rule. So let's jump to the derivative. The derivative of this cosine is negative sine of something, and that something happens to be cosine of cosine of x. And we want the derivative of the inside, which is this. So the derivative of the inside is, let's see if I can do this in a different color here. The derivative of the cosine of x is negative sine of the inside function. Now the inside function is just the cosine of x. And then, finally, we want the derivative of this, which is just negative sine x. So this is a 3-layer chain rule, and the functions are all identical. But as you take the derivative of the outer function, you evaluate it by the inner function, and the inner function for the first level is cosine of x. The inner function for the second level is cosine of x. And then at that point you just have the regular cosine function. Let's take a look at the derivative of this function. We have to look at this as a big picture. The big picture is that there's a product rule. And within the product rule, we're going to apply the chain rule. So let's see how this is going to work. Y prime is equal to the derivative of the first, and let's do this slowly. E to the 5x times the second. That would be the sine 4x plus the first times the derivative of the second. So we need to figure these two things out, and in figuring those two things out we need to apply the chain rule. So derivative of e to the 5x, derivative of e to anything is itself, times the derivative of the power, which is 5, and then we have sine 4x. And then here we have just a regular e to the 5x times the derivative of sine 4x. And the derivative of sine of something is cosine of something times the derivative of something. So you would normally leave your answer like this, but they're asking us to find the second derivative. So in thinking about finding the second derivative, what we want to do is generally simplify the first derivative so we can do a derivative again. If you look at this, this looks like it's going to be two product rules, but if you look at it even closer, we have e to the 5x times sine 4x and the constant e to the 5x times, oh, I guess you cannot combine it. So we'll just have to just rewrite it. 5 e to the 5x sine 4x plus e to the 5x, oops, there's a 4 out there, cosine 4x. Well, we can factor out an e to the 5x if that makes things a little bit easier, but I don't think it would make a difference. Here we're going to do, in this particular scenario, one product rule, but I think it's going to amount to the same amount of work had we not taken this e to the 5x out. Okay, so we'll call this our y prime. Now let's find our y double prime. So it's a derivative of the first times the second. The second is this big old thing. Plus the first times the derivative of the second. Alright, so let's figure out what we need to do. We need to do this derivative, and we need to do this derivative. So the derivative of e to the 5x, we already did that up here, right? It's e to the 5x times 5. And then we leave this alone. plus e to the 5x, and then now we need to take the derivative of this big mess. So the derivative of a constant times something is going to be a constant times the derivative of that something. And the derivative of sine 4x, we already did that one, that's cosine 4x times 4. So that's the first term. The second term is 4 times cosine 4x. So again, the 4 stays out here. The derivative of cosine is negative sine. And then now, after you take the derivative of cosine, you have to take the derivative of the inside. There's another 4 out here. Okay. So I would be happy to leave my answer like this. There's a lot of simplifying that can go on here. But since I don't have to get the third derivative, I would be happy to stop right here. This is a tangent line problem. So let's take a look at this tangent line problem. It says you have an equation, find an equation of the tangent line at the point 1 comma 1 over e. So the first thing we need to do is we need to think about the tangent line. And the equation for any line is y minus y1 is equal to m x minus x1. Now you have x1 and y1 already given to you. Now you just need to figure out what m is. Now for a tangent line, our m is equal to, we know that our m is equal to the derivative, but we have to be careful here. The derivative has to be evaluated at whatever the x value is. So this is an important part of our equation. Let's take our function and find the derivative. And this derivative looks like it's going to be a product rule. That's a derivative of the first times the second plus the first times the derivative of the second. Now here's where you apply the chain rule. Derivative e to the x is e to the x. The derivative to e to the anything is e to the anything times the derivative of the power. So there's an extra negative 1 there. Now we don't want to take this whole thing and put it in for m. That is not good. What we need to do is we need to take our derivative and evaluate it at x sub 1, which is 1 in this case. So I'll use this notation, dy dx, evaluated when x is equal to 1, is equal to, here, wherever c and x, we're going to put a 1. E to the negative 1 times negative 1. So let's see, this becomes 3 e to the negative 1. The negative sign here will be a minus. This is just e to the negative 1. So let's just say 2 e to the negative 1. So that's your derivative. Now let's put it into the equation y minus y1. That's 1 over e. That's also e to the negative 1, by the way. Is equal to the slope. And this is where you put this expression in for the slope, not this expression. And then x minus x1 is 1. And to complete this, we just bring this over to the other side. So y is equal to 2 e to the negative 1, x minus 1, and then plus 1 over e. Again, there's ways to simplify this, but I would just be happy to leave it like that. Alright, let's examine one more problem. It says find a 300th derivative. Now, you probably don't want to take the derivative 300 times for this problem. So what to do is to see if we can take the derivative a couple times, maybe 3 or 4 times, and see if we can find a pattern. So let's try the first derivative, and again, I often say that you don't need to simplify, but since we're finding patterns for derivatives and multiple derivatives, simplifying might be a good thing to do. So, derivative of the first times the second, plus the first times the derivative of the second. E to the negative x times chain rule, derivative of the power, which is negative 1. So here, I would like to simplify this. It looks like e to the negative x minus x e to the negative x. And maybe do one more simplifying, see if I factor out an e to the negative x here. Alright, that's our first derivative. Our second derivative. Let's do this. Derivative of the first, that's e to the negative x times negative 1 times the second plus the first times the derivative of the second. The derivative of 1 minus x is just negative 1. Alright, there's a lot of negative signs and x's and 1's going on here. So let's see if we can power through this. It looks like generally I have 2 terms, and both of these terms have e to the negative x in it, so it looks like we can take that out again. And I have a negative 1 plus x, and then I factored out this e to the x, which left me with a negative 1. So now it looks like I have e to the negative x, and then this looks like a negative 2 plus x, or e to the negative x, and then x minus 2. Now it looks like my variables switched here, and so let's see, I can kind of feel the pattern coming on. Let's see if we can do one more. And after this, hopefully we might be able to guess at a pattern. So let's take a look at this expression. The derivative of the first, e to the negative x times negative 1 times the second, x minus 2, plus the first times the derivative of the second. That's just a positive 1. Looks like I can factor out an e to negative x again. I have a negative x positive 2, and I took out an e to the x, that's positive 1. So I have e to the negative x, and then minus x plus 3. So it looks like we have a pattern going on here. Without doing the actual derivative, we can probably guess that the fourth derivative, this is the notation for the fourth derivative, is equal to e to the negative x. And, let me rewrite this first. E to the negative x, 3 minus x. So it looks like for this one we have a 4 and an x, but it'll probably be in a different order, x minus 4. And then you can probably guess that fifth derivative is equal to e to the negative x, and then 5 minus x. Okay, so let's establish a couple of things. It looks like if the power, or if the derivative is even, then you have an x minus that same whatever derivative that is. So second derivative we have x minus 2, fourth derivative we have x minus 4. If the number of derivatives you're taking is odd, it looks like the odd number comes first and then you have a minus x. First derivative is 1 minus x, the third derivative is 3 minus x. Alright, and I think that's it. That's all we need to know. So for the 300th derivative, f 300 derivative of x is going to be e to the negative x times, now 300 is an even number, so we're going to follow the even pattern. That's second derivative, the fourth derivative, so the x comes first, minus 300. So it looks like that is our solution. Okay, this should give you enough ammunition to attack your homework in WebAssign. You have a lot of homework. I had 40 problems, but I took 5 out, but still 35 problems is still a lot of homework, and the idea behind this is to keep practicing using your derivatives. So when you're doing the problems in WebAssign, it would be a good idea to have another sheet of paper with you to do the scratch work, and also to have the table of derivatives at your side as you're doing the homework, and those things will be really useful for you to get through it. Okay, good luck.